In this video, we're looking at the product and quotient rules from section 2.3 in the textbook, and also looking at higher order derivatives, including derivatives of the trigonometric functions. So first, we'll talk about the product rule. So the product rule says that if we take the product of two differential functions f and g, that product itself is differentiable, and the derivative of this product would look like this. So if we take f times g, the derivative would be the first function times the derivative of the second function, plus the second function times the derivative of the first function. Now, because this is a sum, the order in which you add these two terms doesn't necessarily matter as much because we have the commutative property in addition. So let's go ahead and try a couple of these. So we're given h of x is a product of these two polynomials. So let's find the derivative h prime of x. So h prime of x would be the first, so 3x minus 2x squared, times the derivative of the second. The derivative of 5 plus 4x would just be 4, because we have a constant and then a linear term. And then plus the second function, 5 plus 4x, times the derivative of our first. So the derivative of the first term is just 3, and the derivative of the second term is negative 4x. Now we just do a little bit of algebra. Distributing the 4 in, we're going to get 12x minus 8x squared. And then 5 times 3, that's 15. 5 times negative 4x is negative 20. And then we have a positive 12, so it's minus 8x. And then 4x minus 4x, or sorry, times the negative 4x is negative 16x squared. And then if we look at combining our like terms, we have a 12x and a negative 8x. And we have a negative 8x squared and a negative 16x squared, giving us that our derivative, h prime of x, would be negative 24x squared plus 4x plus 15. And that's how you would use the product rule. So we can go through and try a few more of these. So in this one, we have y prime equals. And looking at this second expression, I probably want to rewrite the square root of x as x to the 1/2 power. It makes it a little bit easier when taking the derivative. So we'll write this term as x to the 1/2 minus 1. So y prime equals the first part of our function, right? The first part of the product, 2x minus 3 times the derivative of the second. So that's going to be 1/2 times x to the negative 1/2 plus the second part of our product, x to the 1/2 minus 1, times the derivative of the first part of our product, which is just 2. And now we can just distribute and do some simple algebra. So y prime equals 1/2 times 2, that's going to be 1. X times x to the 1/2, so that's 1 minus 1/2, which is 1/2. So we're just going to get x to the 1/2. That's going to be minus 3/2 x to the negative 1/2. 2 times x to the 1/2 is exactly that. And then 2 times negative 1 is minus 2. Now in this, we have some like terms here that we can combine. And that gives us 3x to the 1/2. So y prime is 3x to the 1/2 minus, and then this negative exponent can move to the denominator. So 3 over 2 times x to the 1/2 and then minus 2. And if we felt so inclined, we could make these x to the 1/2 into radicals. So we get 3 rad x minus 3 over 2 rad x minus 2. And that would be the second one. Part C, if we want to take the derivative, so y prime equals, so it's the first part of our product, x squared, times the derivative of our second. We know the derivative of e to the x is just e to the x. Plus our second part of our product times the derivative of the first. So the derivative of x squared is 2x. And then just simplify, we get that y prime equals x squared e to the x. And then let's say plus 2x e to the x. Now this last one, we just have to use some of the rules that we know. Anytime you take a sum or a difference of two functions, it's just the sum or difference of their derivative. So this one is just going to be, this derivative is just going to be subtracted from what we get as a after we do the product here. So we get that y prime equals, so the first part of our product is going first. The derivative of sine is cosine, and then plus the second part, sine of x, times the derivative of the first part of our product, which is 8x. And then all of this is going to be minus 7 times the derivative of cosine is negative sine of x. And so then we have that. And then just simplify. So we get that y prime equals 4x squared cosine of x. We can bring the 8x in front, so plus 8x sine of x. And then a negative 7 times a negative sine is going to be plus 7 sine of x. And that would be the derivative. And this is how you use the product rule. This is something that comes up a lot and we have to use very frequently. So it's really good and important to know. The next rule we're going to talk about is the quotient rule. So if we have the quotient f divided by g of two differential functions, f and g, it will itself again be differentiable at all values of x where our denominator is not 0. And to find the derivative of this quotient, it will look like this. So basically you take the denominator function times the derivative of the numerator minus the numerator's function times the derivative of the denominator, all divided by the derivative function squared. Again, g of x is not allowed to equal 0 because that would make our denominator 0 and this undefined. Now, one thing that's important to note is because the numerator is a difference, the order does matter, unlike what we had in the product rule where it didn't really matter because of the commutative property. We know that commutative property does not apply in subtraction, so we need to make sure that we set up the numerator correctly when we're doing the quotient rule. So let's go ahead and try a couple examples of this. So we want to use the quotient rule to find the derivative of each function. So the first function we're going to take the derivative of is f of t. So f prime of t equals, so it's the denominator function, 1 minus t, times the derivative of the numerator. The derivative of 9 is 0, and then of negative 7t is just negative 7, minus the numerator's function, 9 minus 7t, times the derivative of the denominator. Again, that's just going to be negative 1, because this derivative is 0, and we have that there. All of that divided by our denominator function squared. Doing a little bit of algebra, we get this, if I distribute this negative in, I get negative 9 plus 7t here. So I get that f prime of t equals negative 7 times 1 is negative 7, plus 7t. A negative times a negative is going to make that positive 9, and a negative 7t, all divided by 1 minus t quantity squared. We see that we have a negative 7t and a positive 7t that will cancel, and we get that f prime of t is negative 7 plus 9, that's 2, divided by 1 minus t, all of that squared. So that is the derivative of our first function. Our second function, again, I would probably rewrite the square root of t as t to the 1/2. And then we can just call this t to the 1/2 all divided by t minus 1. So if we're going to take the derivative of r here, so we have r prime of t equals the denominator's function, t minus 1, times the derivative of the numerator, 1/2 t to the negative 1/2, minus the numerator's function, t to the 1/2, times the derivative of the denominator, which is 1, all divided by our denominator squared. So t minus 1 quantity squared. Multiplying 1/2 t to the negative 1/2 with t to the first, we can just add the exponents. So we're going to get 1/2 t to the 1/2. So 1/2 t to the 1/2, and then minus 1/2 t to the negative 1/2, and then minus a positive t to the, or sorry, and minus a t to the positive 1/2. And we have some like terms there. Again, all of this is still going to be divided by t minus 1 quantity squared. So putting all of this together, 1 half t to the 1 half minus t to the 1 half is going to give me negative 1 half t to the 1 half minus 1 half t to the negative 1 half, all divided by t minus 1 quantity squared. So I can factor out this 1 half. So I have 1 half times this whole thing. So I have negative t to the 1 half minus t to the negative 1 half all over t minus 1 quantity squared. Now with these t to the 1 halves, really they're like radicals. So what I want to do is I want to try and get them in terms of whole powers of t. So I'm going to multiply the numerator and denominator by t to the 1 half over t to the 1 half. Because when I multiply t to the 1 half by t to the 1 half, I get t. And then t to the 1 half times t to the negative 1 half just gives me 1. So I end up with negative t minus 1. This 2 can be put in the denominator. So 2 times t to the 1 half, all times t minus 1 quantity squared. So this right here would be our derivative of what we started with. So that's the derivative of r. Sometimes when we're trying to take the derivative, we need to rewrite an expression before we can differentiate it. So what I'm going to do is I'm going to rewrite this as a sum of two terms with x cubed in the denominator. So I have f prime of x equals 1 over x cubed plus x squared over x cubed. This helps us because we can do some simplifying, right? X squared divided by x cubed would be 1 over x. And I'm actually going to rewrite this with some negative exponents because then I can just use the power rule to take the derivative here. So I'm going to get x to the negative third plus x to the negative 1. So now when I want to take this derivative, f prime of x, it's going to be negative 3 times x, subtracts an exponent, so to the negative 4 power, negative 1 times our power function, so minus 1 times x to the negative 2. And I can move these negative exponents into my denominator. So f prime of x equals negative 3 over x to the 4th minus 1 over x squared. So you could leave it here. If you wanted to put them back in terms of a single with a common denominator, we could multiply these by x squared. And that would give us something like negative 3 minus x squared all over x to the 4th. But there's no real need to do that. It's just sometimes might be nice to have this, or you need to be able to recognize that these two are equivalent. So let's go ahead and try and rewrite this next expression. So this is going to be y equals, with the difference of squares, I'm assuming I'm going to have to factor. So t plus 5 times t minus 5, all divided by t minus 5. So in doing that, I can see that this t minus 5 is going to cancel, allowing me to rewrite my expression as just t plus 5. So when I take this derivative, which is a pretty nice one, I get that y prime is just going to equal 1. The derivative of t is just 1. The derivative of 5 is 0, giving me this. And then the last one, I'm going to rewrite this by taking this x squared and moving it into the numerator using negative exponents. So I'm going to have 10 over 3 times x to the negative 2. And so when I take the derivative of this, y prime equals, I can just use the power rule. So negative 2 times 10 thirds is negative 20 thirds, x to the negative third, and then get rid of my negative exponents. So I have y prime equals 20 over 3 times x to the third. Sometimes we need to take a higher order derivative. Basically, a higher order derivative just means we take the derivative once, that's our first derivative, take the derivative of our new function again, that's called the second derivative, and then take the derivative of our new function again, that's the third, and then so on. We can keep repeating that process as long as the result is differentiable. And the notations that we use are similar to what we had when we were just taking the derivative, right? We have y prime, f prime of x, dy dx, and then this is saying take the derivative of f of x, take the derivative of y with respect to x, and such. The two apostrophes up here is double prime, so that's the second derivative. And you can see in here it's like d squared y over dx squared. This is how we would denote the second derivative using this notation, and then the third derivative would use this notation. One thing to note is after the third derivative, we start using y to the nth in parentheses because we don't want to have like a big long string of primes in there. So it'd be like y to the fourth in parentheses, or f to the fourth x, like in parentheses. And those denote higher order derivatives. So let's go ahead and take a look at how we would evaluate some higher order derivatives. So it's asking us to find the first four derivatives of the function y equals x cubed minus 5x squared plus 2. So the first derivative, we can just use the power rules and then the sum and difference rules. So for the first term, we're going to get 3x squared. For the second term, it's going to be 2 times negative 5, which is negative 10, times x to the first. And then the derivative of 2 is just 0. So this is our first derivative. To get the second derivative, we just take the derivative of the first derivative. And so we have 2 times 3, that's 6x. And then this is to the first, so we get minus 10 times x to the 0, which is just 1. So this is the second derivative. To take the third derivative, we just take the derivative of this. So we're going to get just 6, because the negative 10 has a derivative of 0. And then the fourth derivative, we take the derivative of the third derivative to get 0, because the derivative of a constant is just 0. So these are the first four derivatives of our function y equals x cubed minus 5x squared plus 2. Often we will also deal with having to take the derivative of trigonometric functions. We've already seen the derivative of the sine and derivative of the cosine, but we now have the derivative of our four other trigonometric functions. So the derivative of the tangent is secant squared. The derivative of the cosecant is negative cosecant squared, negative cosecant x cotangent x. Derivative of secant is secant x tangent x, and then the derivative of the cotangent is negative cosecant squared. One thing that is useful to note is when you take the derivative of all of the cofunctions, you result with a negative in your answer. So cosine is negative sine. Cosecant is negative cosecant x cotangent x. Cotangent is negative cosecant squared x. So that's something helpful to remember. So when you're taking the derivatives, the cofunctions give you a negative. So let's try a few derivatives using the trigonometric functions. So the first one, we want to try and find the derivative of this function here. So we're going to have the power rule, and then we're just going to be subtracting the derivative of the cosecant. So y prime equals, we have 6x here, minus, and we said the derivative of cosecant x is negative cosecant x cotangent x. Subtracting a negative is going to make that positive, so we have 6x plus cosecant x cotangent x, and that would be y prime. To find the derivative here, we're going to have to use the product rule. So we have y equals the first function times the derivative of the second. So the derivative of cotangent was negative cosecant squared x, and then plus the second function, cotangent x, times the derivative of the first part of our product, which is 3x squared, and then just simplify. Oh, that's y prime, sorry. So y prime would be negative x cubed times, let me fix that, negative x cubed times the cosecant squared of x, and then plus 3x squared cotangent of x. So that would be the derivative here. And then for this last one, we could end up using the quotient rule, but we could also recognize that this can be rewritten as 1 over the secant of x minus the cosecant of x divided by the secant of x. And this makes our life a little bit easier because we know that 1 over the cosecant is just the cosine. So that's the cosine of x. Cosecant of x is 1 over the sine of x. And then the secant of x is 1 over the cosine of x. which means this term here would end up being the cotangent of x. So it's minus cotangent of x. And now we can just take the derivative of what we have here. So we end up with y prime equals, we know the derivative of the cosine is negative sine of x, minus, and then the derivative of the cotangent is negative cosecant squared x. So simplifying, we get that y prime is negative sine of x. Multiplying the two negatives gives us plus cosecant squared x. And that would be the derivative of what we started with.